All right, we're going to work through an exam style question on the pH of salt solutions. So the premise of these questions is that we dissolve some salt, so something that is a metal and a non-metal, or maybe a polyatomic is in there, but something that's going to dissolve into its component ions. And then we need to assess, do those ions react with water in a way to make some H plus or some OH minus, which would of course then impact the pH of the solution. So I'd like to look at these problems by first looking at my component ions, like what does it break into, and then do those ions have a reaction with water? All right, so in this question, it's framed as, are we making an acidic solution? But I'm going to go through and answer the pH of each one. So let's look at this first one. So we're looking at sodium acetate, which is going to be Na plus and CH3COO minus. Na plus is one of our group 1 metals that is not densely charged enough to draw in protons from water, and so it winds up not having an impact on the pH. But CH3COO minus, that is the conjugate base of a weak acid, which is acetic acid, CH3COOH. Okay, I know that's a weak acid. I see that there's a proton there. And I know that CH3COOH is not a strong acid. It's not one of the 6 strong acids that we've had you memorize. So it must be a weak acid. The conjugate base of a weak acid is itself a weak base. So when that gets put into solution, it will react with water. Some of that will pull a proton off and we'll make some of the conjugate acid, the CH3COOH, and some OH minus. That is what tells us that this is going to be a slightly basic solution. So this is not one of our answers. All right, now we look at potassium fluoride, KF. That's going to be K plus and F minus for the same reasons that sodium plus wasn't going to have an impact on our pH. Potassium plus also is not going to have an impact. It's group 1 metal, not very densely charged. It's not one of the transition metals that has an impact on the pH. So that doesn't do anything. F minus is, again, same story, the conjugate base of a weak acid. And so we're going to have a similar reaction where we're going to produce a little bit of HF and some OH minus. This is the important actor here. That means we're going to have a slightly basic solution. Okay, so KF is also not an answer. NaCl, we know N plus does not do anything. Cl minus also doesn't do anything in solution. So just keep track of what we're saying here. Na plus and Cl minus. Cl minus is the conjugate base of a strong acid. So HCl is one of our strong acids. So this is a negligible base, which means that a solution of NaCl I would expect to be neutral. All right, next we have calcium nitrate. All right, so we look at calcium 2 plus and then 2 NO2 minuses. Same story. This is going to that's group 2. It doesn't have an impact on the pH. It's just not densely charged enough. NO2 minus, that is the conjugate base of HNO2, which is a weak acid. So I'd expect this to be basic. For the same process and same reasoning that I had for the first 2 answers. And now we finally get to an answer that I think is going to give us an acidic solution. So ammonium chloride. You need to remember that ammonium is NH4 plus, and it's going to hold on to that extra proton. That is the conjugate acid of NH3 of ammonia, which is a weak base, which means that this must be a weak acid. So once ammonium chloride dissolves in solution, I'll have some NH4 plus. That dissociates slightly, some small equilibrium constant, but significant enough that we generate some extra H plus. That means we're going to have an acidic solution. So that's a correct answer. And then lastly, we have iron 3 chloride. So Fe3 plus and 3Cl minus. This is finally, not a group 1 or group 2 metal, it's in that D block, and it has a very high charge density, so much so that when it goes into solution, to stabilize that 3 plus, water molecules come circle around it, and they donate their electron density to the point where we're really pulling, that oxygen is going to be really pulling on some of this electron density from hydrogen, from the hydrogen, and it becomes really partially positive. So much so that another water comes along and swoops it. Okay? And we wind up with generating some H3O plus, which is what makes these solutions a little bit acidic. So if we're looking for acidic salt solutions, we're looking for probably a cation that is a charged nitrogen species like ammonium or methyl ammonium, something like that, where a nitrogen weak base has already taken a proton. That's exactly what could give a proton back a little bit. And then these transition metals that are really have really high dense charges. So Fe3 plus is one, aluminum 3 plus, nickel 2 plus, zinc 2 plus. Really along, we often will pull out some of those 3D transition metals that have very high charges for questions like this.